Welcome to Digital Signal Processing Lab. And today we are going to conduct another experiment on MATLAB. So, the objectives of this experiment is written here. You can read it out. So, the objective is to generate a discrete time signal xn, which is equals to cos 0.4 pi n. And we have to plot this signal in time domain, and we have to also obtain its spectrum. The second objective is to downsample the signal xn by a factor of 2. And again, we have to get the downsampled signal plot and its spectrum. And then again, we have to go for the interpolation of the downsampled signal by the same factor of 2. And then again, we have to get the interpolated signal in time domain, and we have to find out its spectrum. So first, to begin with this first objective, okay, so we have to generate a discrete time signal. Okay, so let's try to see how this discrete time signals can be generated. So since it is a cosine signal, okay, it is a discrete cosine signal, so let's start with it. So suppose that if we are having any continuous time signal xt with amplitude a and certain frequency omega t, okay. So normally this omega can be written as 2 pi fmt, okay. And then because this signal must be periodic signal, so it's because it will be periodic, then it's time period we can calculate, and that will be t equals to 1 upon fm, right? So where this fm is obviously an analog frequency, right? So now when we want to obtain the discrete time signal, okay, discrete cosine signal, that time we have to sample this signal to get the xn values, right? So to get that xn values, here this time index t, which is here in this case, it is a continuous value. It is taking the continuous value. But in the case of discrete time signal, this should be discretized at a certain regular interval of time. Okay. So here this t will be transformed to some n multiplied with capital Ts, where this n denotes you some integer values. It may be starting from 0, and then it will go like 1, 2, 3, 4, 5, and so on. Okay, and this Ts represents you the sampling interval. Okay, and this way we are going to get this signal xn. So obviously this sampling interval Ts will be related with the sampling frequency, and this sampling this Ts is equals to 1 upon Fs. Okay, so here I have just replaced this Ts by 1 upon Fs, and this way we will be able to see this particular expression xn equals to a cos 2 pi fm multiplied with the n upon Fs. So now here we can see this entire factor 2 pi fm upon Fs, this we can replace by another symbol like this omega. Okay, this omega. So here this omega is nothing but it is 2 pi fm upon fs. Okay, and normally this 1 upon fs we can write it as sampling interval ts, and here this 2 pi upon fs can be 2 pi sorry, it is 2 pi fm can be written as omega, right? So this way we can represent this signal, where this particular omega in the left hand side, this represents you the digital frequency, and this particular omega represents you the analog frequency. Okay, so this will be again analog frequency in the radians. Okay, and here this particular frequency will be called as the digital frequency. So first of all, we have to look at what should be the range of this digital frequency for various range of this particular omega. Okay, so here we know that because this omega is related by this particular expression 2 pi fm upon fs. Okay, so normally we know that if we sample any continuous time signal from its sampled version, if we wish to get back the original continuous time signal, then it is required that this sampling frequency should be greater than or equals to 2 fm. Okay, it cannot be less than 2 fm. It is, if it is less than 2 fm, this sampling frequency In that case, there will be a aliasing effect, and the spectrum of the signal will be overlapped, and while doing the filtering operation, this overlap cannot be avoided. Okay, and therefore we cannot reconstruct the signal, and therefore this fs must be greater than or equals to 2 fm. So theoretically, we can see this fs, its maximum value can be equals to infinity. Okay, so if it is infinite, here we can see that in that case, this omega minimum value will be equals to 0, because we can see that this omega is inversely proportional to the sampling frequency. So if we increase the sampling frequency, or if we take the maximum possible value of the sampling frequency, that time this omega minimum will be equals to 0. If we strictly taking this fs equals to 2 fm, okay, and that time we will be getting this omega maximum, and that will value you can evaluate by substituting 2 fm over here. So this 2 fm will be cancelled out, and we will be left out with the pi. So this value is omega maximum equals to pi. Okay, so this is the range of your omega, okay, which is your digital frequency, and that range will be from 0 to pi. Okay, so that we have to remember. So now what we can see is this way, this continuous time signal a cos omega t is now converted into a cos omega n, right? So here we have to see the problem which is given, xn equals to cos 0.4 pi n. So you can see this xn equals to cos 0.4 pi n. So here we can see this digital frequency omega is nothing but 0.4 pi. Okay, if you take the value of pi, and if you multiply, this value will be coming out as 1.2566, which is same as your omega into ts, right? So at present, we have not told what is the value of sampling frequency in this case. Okay, so right now we have to generate this particular signal, right? So you remember that if we wish to have this discrete time signal to be periodic, okay, one thing that you must remember, this is a continuous time signal which is always periodic. Okay, it will always be periodic signal. But once we will sample this continuous time signal, and we have obtained this discretized cosine signal, that time it may or may not be periodic. Okay, it is not need to be periodic, I mean to say, right? So it may be periodic, it may not be periodic. So the sufficient condition, it will be periodic if 2 pi divided by this value of omega. Okay, if it is a rational number, then it will be a periodic signal, right? And this periodicity we can find it out by evaluating this particular expression. So n equals to 2 pi upon omega, and multiplied with a certain value of r. R will be an integer number. We have to take this integer number to a minimum value, such that this entire product will become an integer value, right? So here we can see this 2 pi upon omega. If you substitute here 0.4 pi, this pi and pi will be cancelled out, and it will become 2 upon 0.4. So it means this ratio will become 5. Okay, so here we have to choose r equals to 1, right? So because this ratio is 5, it means that this periodicity in terms of number of sample for the given cosine signal, this n is equals to 5. So it will be periodic with number of samples equals to 5. Okay, so that we have to see while plotting, right? So first we will be seeing how to plot this signal, and obviously, because we have to also get its spectrum. So to get the spectrum, what we can do is we can have this discrete time Fourier transform definition, right? So if we have any signal xn, then we can calculate its discrete time Fourier transform by following this particular expression, right? So here it is, n is varying from minus infinity to infinity, xn e to the power j omega n, where omega is the discrete frequency. And obviously this discrete frequency will vary from 0 to pi. And normally it is found that this is the property of your discrete time Fourier transform, that this x is a omega will be periodic with 2 pi. Okay, so its spectrum will be a periodic spectrum, that you have to remember, right? It will be a periodic spectrum. So let's say that if the signal xn is a causal signal, right? If it is only defined for n equals to 0 and greater than 0, then this summation will go from n equals to 0 to infinity. And that time you can expand this equation. So if you expand this expression, you will be getting this type of expression, okay? x0 plus x1 e to the power minus 2 minus j2 omega, x2 e to the power minus j3 omega, and so on. Okay, so this way we can have this it's a Fourier transform, right? Fourier transform of your given discrete signal. So the same thing we have to also use in the MATLAB. So let's try to see this, how this can be obtained, okay, onto the MATLAB. So we will be first try to implement this particular expression, okay, this expression we'll try to implement. So here I have written this code onto the MATLAB. Here you can see. So here in the first case, we can see this code have been written for to generate the discrete time signal and to get its frequency spectrum. Okay, so the first line is CLC and clear as usual. Okay, and here I have generated the time index, right? So here I am defining the time index array. It is 1 to 10,000 such samples we are going to generate. And here we have generated the signal xn, right? So this is our signal xn cos 0.4 into pi into n. So here you can see this periodicity. If you calculate n equals to 2 into pi divided by 0.4 into pi, it will be coming out as 5. Okay, so its periodicity will be 5. So because we have taken n equals to 1 to 10,000 samples, I'm not going to plot all these 10,000 samples, okay? So just to see this signal, the discrete time signal, I have just taken first 20 samples. Here you can see in the stem plot, I have just plotted first 20 sample of your generated signal in this X, okay? So only first 20 samples. So this way, if you write 1:20, you will be able to see your first 20 samples, right? So that I will be executing and then I will show you. So here we can see in the next code I have written for generation of the spectrum of the given signal, right? So to generate the spectrum, we are having this particular command, okay, in MATLAB. So this is a frequency Z, okay? So this particular frequency Z command we have to use, right? So if we use this frequency Z, then we will be able to get the spectrum of any discretized signal, right? So here I will be just typing this frequency Z on MATLAB command so that you will be able to see what is this frequency Z command. Okay, so if we type help and here frequency Z, you can see this definition of this particular command. Okay, so this is your frequency Z command, which is frequency response of digital filter, right? So here, if you use this particular command frequency Z, it will be going to give you two different values. Okay, so one is the frequency response, and it will be giving you a corresponding frequency values, okay, at which this frequency response has been calculated. So as I have shown you in this slide that normally discrete time for a transform, if you see, because omega will be a continuous variable in this case, but for the plotting in the means on MATLAB, we cannot take the continuous values, okay? So again, we have to discretize this omegas, right? So that discretization we have done. So once we'll be doing this discretization of the omega, so this omega will be discretized in between 0 to pi, okay? So that time, if you use this particular command frequency Z, okay, so here we are going to get a vector of omegas, right? So it will be like n number of omegas at which we are calculating this frequency response. So basically what happens this, because its maximum value is pi, omega is maximum value is pi. So this pi is going to be divided by capital N, right? So that is going to give you n point complex frequency response, okay, vector h and n point frequency vector w in radians per sample of the filter. So here you can see we are having this two coefficients b and a. Okay, so these are the coefficients which are the these are the vectors. B and A are the vectors which contains the coefficient of this numerator polynomial and denominator polynomials. Okay, so if we have any digital filter, in that case, this digital filter will have a certain numerator polynomial and denominator polynomials. So that time this B will be containing these values, B1, B2, up to Bn plus 1, right? Similarly, this A will be containing these coefficients, right? So basically here you can see when we are using this frequency Z command, okay, in our case, what we have done is we have taken the first, like here you can see, because here if you see this format, okay, first we have to write B. Okay, so what is this B? This B is the B is the vector which contains all the coefficients of your numerator polynomials, right? So here if you see this particular code, okay, if you see this particular code here, it is written as x comma 1 and then comma 512, right? So what this 512 is the capital N, okay, as per this command, okay, means as per this particular format, right? So here this capital N is equals to 512. It means that we are dividing the whole frequency response, means 0 to pi, at equidistance of total number of n points. Okay, so this pi will be divided by capital N, and then that value will be equally spaced from 0 to pi. Okay, so that will be creating the vector w. So now why we have put it this x in this particular command, okay, we are writing x over here and then 1. So this 1 is corresponds to coefficient of your A vector, okay, this A vector, right? So now you just try to make a comparison from this definition and from this discrete time Fourier transform. So here this x e j omega can be also be written as this is the numerator polynomial divided by 1. Okay, so if you write this way, these coefficients x0, x1, x2, x3, this will become the coefficients of your vector B, right? And then divided by 1. So the coefficient in vector A will be equals to 1. Okay, so the same thing has been implemented by using the frequency Z command. Okay, so if we have any filter and if we have the B and A coefficient, we can substitute it there, and then we can find out the frequency response of the filter. And even if we have any signal, okay, the same frequency response can also be calculated, provided that we have to give the signal itself at this particular instead of giving the B. So at the place of B, we have to apply the X. And then at the place of A, we have to give this value equals to 1. Okay. So here I have chosen this n equals to 512 points. Okay. And here this whole means it will be giving you frequency response from 0 to 2 pi. Okay. As I said that this Fourier transform is normally periodic with 2 pi. Okay, so if you don't write whole here, okay, let me remove this first. Okay, if you don't write whole there and if we execute this, okay, so let me comment these lines also. It is not required at this moment. So if we execute this code, okay, here we can see the result. Okay, so first of all, we have to see this discrete time signal that we have generated. So this is our xn. Okay, so this is the xn that we have generated, right? So here you can see, because I have shown that the periodicity of this xn is equals to n equals to 5. So it means after 5 samples, the same sample is going to be repeated. So here you can see this periodicity. Okay, this is our first sample, right? Its value is 0.309. So after 1, 2, 3, 4, and again this fifth sample is the same sample. Okay, its magnitude is same. Okay, do not confuse with this sample, right? Because this sample is having the same magnitude, right? But again, if you see, this sample is repeated after, this is the third sample. Okay, so 1, 2, 3. So this periodicity, if you consider to be 3, then again, the same sample should be repeated after 3 sample, right? So if you see, if you count the samples from here, 1, 2, 3, we are not going to get the same sample again. And therefore, 3 cannot be its periodicity. And even we have also calculated this periodicity is equals to 5. Okay, so this sample is here, and after 5 sample, 1, 2, 3, 4, 5, we are again getting the same sample. Again 1, 2, 3, 4, 5, again we are going to get the same sample, right? The same periodicity you can also means observe for any other rest of the sample. Okay, for example, if you wish, you can see this particular sample, right? So again, here it is minus 0.809. Okay, so the same sample will be repeated after 5 samples. So 1, 2, 3, 4, and again fifth sample is the same sample, right? So this way you can identify its periodicity, right? Again, for this sample, if you see, this is y equals to 1. So here again, you can count 1, 2, 3, 4, 5. So this is the fifth sample. Again, the same sample is repeating, right? So here we can easily see its periodicity. It is a periodic signal with periodicity of 5 samples. Okay, and we have plotted the total 20 number of samples, right? So now here we can see the spectrum. Okay, so here you can see this is spectrum. So as I said that this is spectrum that we have calculated. Okay, we have calculated the spectrum of this particular cosine, discrete cosine signal. So here its digital frequency is equals to 0.45. Okay, 0.4 into pi. Okay, so this spectrum within this spectrum, we are expected to get the peak at 0.4 pi. Fine. So here you can see we are getting this peak value, right? If you see this spectrum, we are getting a certain peak value. Okay, and this peak value is coming for x equals to 1.257, right? X equals to 1.257. So that you can calculate. So if we take this value 0.4 multiplied with the pi, okay, if you multiply it with the pi, you will be getting this value equals to 1.2566, right? So at this particular frequency, we are supposed to get the peak, okay, because our digital frequency is 0.4 pi. Now it is also we have to see what is the vector of your W. Okay, as I said that this xz is nothing but your frequency response. Okay, frequency response of this particular discrete signal, and this is the frequency vector. Okay, this is the frequency vector W. So as I said that this 0 to pi will be equally spaced value. Okay, and there will be such 512 points. So we can see this. If we divide this pi, okay, by 512, okay, we will be getting this value equals to, sorry, so it should be 512 divided by, it should be divided by 512. So this value is coming out as 0.0061. Okay, so now we can see this W vector. So if we see this, there are total 512 such points, and here we can see this W values. Okay, so let me open this. Okay, so these W values, you can note down these values, right? So this is W equals to 0, 0.0061. Then again, it is the step size of 0.0061, and then again it will be added to this particular value. So it will be 0.0061, 0, 1, 2, 3, and so on. Okay, so the step size is 0.0061. So that we can verify here. Okay, so easily we can verify. And obviously it is going to have a maximum value which will be pi or less than pi. Okay, so here you can see this maximum value of your omega. So that value is coming out as, here we can see it will be here we can see this value, maximum value. Okay, it is 3.1355. Okay, so how this value we are getting? So if you wish, you can do this. You can take pi and you can subtract this value 0.0061. So I hope this value will be the maximum value, right? Okay, so 3.1355. So this is the maximum value, total 512 points, including the zero. Okay, so this is what we have got. So here we can see in this case, what we have done, we have generated this xz variable and w corresponding w values on means omega values, and then we have gone for the plotting. Okay, so this is our absolute value of our xz we are plotting, because it is going to be a complex values, right? So we have to take its magnitude. To calculate its magnitude, there is a function abs. If you calculate this abs, it will be giving you the absolute value, its magnitude value. Okay, so this way we have to get this plot, right? So now we have done our first part. Okay, first objective, and now we have to go for our second objective. What is the second objective says? The second objective says we have to downsample the x and by a factor of 2. So first of all, we'll try to understand what is this downsampling. Okay, so normally in the downsampling, what we do is whatever be the sampling frequency of your original signal, we have to reduce the sampling frequency by a factor of 2. Okay, and then we have to obtain the samples, right? So this is the meaning of downsampling, right? So we have to reduce the sampling frequency by a factor of 2. So what we have to do is we have to just you try to see this with an example, right? So what we actually trying to do. So for example, let us suppose that we are having any signal. Okay, so suppose if we are having any signal cos 2 pi 100t, this is our continuous time signal. Okay, and here we can see this continuous time signal is having its analog frequency equals to 100 hertz, right? So if we go by the method of sampling, okay, if we sample this signal and let us say that this sampling frequency is 100 hertz, 500 hertz. Okay, here I have taken 500 hertz. Okay, and then this t will be replaced by n upon 500. Okay, so once we'll be choosing 500, we can see that this value, if you calculate, then you will be going to get cos 0.4 into pi into n. So this is one of the way of generating this signal. If our signal originally is of 100 hertz signal, right? So this way we can generate this cos 0.4 into pi into n. Okay, discrete cosine signal. But suppose if we wish to downsample the signal by a factor of 2. So in that case, what I will do, if we go by starting of sampling, then what I will do is I will be taking the sampling frequency equals to 250. Okay, so if you take the same signal again, and if you reduce the sampling frequency by a factor of 2, it will be 250. Then the signal that you are going to get is cos 0.8 into pi into n. Okay, so this way we are going to get this particular signal, right? If you downsample the signal. Okay, so instead what we generally do in the case of MATLAB, okay, if we wish to downsample any signal by a factor of 2, what we can do is we can simply skip one samples, right? We can simply skip one samples. If the downsampling factor is 2, then we have to skip one sample, and if our downsampling factor is 3, then we have to skip 2 samples. If it is downsampling factor is 5, we have to skip 4 samples. Okay, so here you can see in the MATLAB I have written this code. Okay, so here you can see this line. Okay, so let me remove this comment line. Okay, so I'm just removing it. So what we can have is, I can just directly write this downsample. Okay, so which signal we have to downsample? We have to downsample this X, right? So I have written this signal X, and we have to downsample it by a factor of 2. So here I have written this factor 2. Okay, so this downsampled signal will be now stored into vector Y. Okay, and then we have plotted again first 20 samples. And then again, I have calculated the frequency response of this downsampled signal Y. So here I have written Y. Okay, and then I have similar expression I have written to get the frequency response. Okay, so here I wanted to show you that what is the difference if we don't write whole and if we write like this. Okay, if we don't write the whole here, because in this expression I have not written whole, and here I have written the whole. Okay, so here you can just concentrate upon this particular graph. Okay, this graph, the maximum value I have shown is that it was coming out as pi. Okay, less than, a little bit less than pi. Okay, because this maximum value of omega is up to pi, so it cannot go beyond that if we don't type whole. But you remember that as I said that the discrete time Fourier transform is periodic with 2 pi. Okay, so if we write whole, then what it will do is it will also plot the spectrum up to 2 pi. Okay, so you must be knowing that this is the only positive part of your frequency component. So if you plot the negative part also, then as we can here we are getting this peak at 1.257. A similar peak you are also going to get at the negative side, minus 1.257. Okay, so there will be one spectrum at the negative side also. Okay, and the same, this spectrum is going to be appear across 2 pi. Okay, it will be appear across 2 pi, and then again 4 pi and 6 pi and so on. Okay, so that way this spectrum is going to be a periodic spectrum, right? So that we can observe now if we execute this code. So let me run this code. So now here you can first observe this. Okay, so let me show you this result, right? So let me show you this 2 result first. Okay, what is your downsampled signal, okay, in time domain, and what was your original signal? So here you can see this original signal. Okay, so here we have this original signal. So if you see this original signal, okay, and here is the downsampled version, then you can make a comparison between the two. Okay, so what is this difference that we can analyze here? So you can see this, this is our first sample. Okay, 0.309, and again here we are having this first sample. Okay, 0.309. Now because this original signal is downsampled by a factor of 2, it means we have to skip one sample. Okay, so now this particular sample will be skipped. Okay, and the next sample will be retained, right? So this sample is actually being retained here. Okay, you can see this particular sample minus 0.8090. This sample has been retained. Now again this sample will be skipped, the next sample, and then again this sample will be retained. Okay, so this particular sample you can see here. Okay, it is retained, right? So here we have this particular sample, right? Then again after this sample will be the next sample will be skipped, and then this sample will be retained. Okay, so here you can see after this sample we are getting this sample directly. So the difference is that if it is downsampled by a factor of 2, the original signal, there will be one sample that we have to skip. Okay, and we have to choose the next sample. So this way we are getting this particular sequence, right? And now you can see from this calculation, as I said, that because after the downsampling, this discrete frequency will become 0.8 pi. Okay, so when you see its spectrum, okay, if you see this spectrum, of your original signal, right? This was the original signal, right? And if you compare the spectrum of your downsampled signal, okay, here you can see this downsampled signal, right? So here you can see this spectrum, right? Now this spectrum is coming out at 0.8 pi. Fine. So here you can compare this value. Okay, this value was coming at 1.257, and now this must be coming around 2.5. Okay, so you can see this value 2.51. Okay, and one more interesting thing is that why we are getting these two peaks, right? But you can see in the code I have written whole. Okay, here I have written WHOLE whole. So it means that this spectrum will be plotted up to 2 pi. Okay, so this range you can also see. Okay, in the first case, this was actually going up to pi. Okay, here you can see this value up to 3.11 or so. And here this value is going up to somewhere around 6. Okay, so it is going up to 6. So it is completely for the 2 pi duration it has been plotted. So as I said that because the spectrum there will be a negative part. So once we are going to get this 2.51, so there will be a spectrum at minus 2.51. So if we get shifted around 2 pi, then you can subtract from 2 pi to this particular value. So if you see what should be this value, it should be 2 pi. You can multiply here 2 pi. 2 pi minus, it should be, this value should be 0.8 pi. Okay, so if you subtract this value, you will be able to get this value. Okay, 3.769. So another spectrum that we are going to get is around 3.7699. Okay, so that value we can note down. It's 3.767. Okay, so at this point we are going to get another spectrum. Okay, and you must be remembering that this is coming due to we are plotting the entire spectrum up to 2 pi. Okay, so therefore we are getting this particular spectrum, right? And because the spectrum is periodic, right? So this way we are going to get the spectrum of our downsampled signal. So now we can move on to our third part. So in our third part, what we have to do is we have to interpolate the downsampled signal by the same factor 2. And then again, we have to plot the interpolated signal and then its spectrum. Okay, so the meaning is the sample that we have lost during the downsampling process, we have to try to reconstruct the those samples. Okay, we have to reconstruct those samples. So those samples that we have lost, okay, that sample we have to reconstruct again by using the interpolation method, right? So to do that, we have written this code here. Okay, so you can see this code. Okay, so let me close this figures. Okay, let me close this figure. So here I have written this code. Okay, a very simple code we have written. So here you can see this, sorry. So to remove this comment first, okay, so let me remove this comment. So here I have using this particular command interpolate. Okay, it is enter p, means it is interpolate this signal. Okay, which signal we have to interpolate? The downsampled version. Okay, this is your downsampled signal y. So that signal we have to interpolate by a factor of 2. Okay, so once we'll try to interpolate, okay, then it will be trying to interpolate the signal by following the low pass filtering method. Okay, so it will be trying to increase the sampling rate. Okay, it will try to increase the sampling rate by inserting the extra samples. Okay, so here you can type this interpolation. Okay, interp, and then you can see what is the definition of interp p. So if you see this, you will be seeing this all explanation. Okay, so enter p resample data at higher rate using the low pass interpolation method. Okay, so it will be trying to interpolate the missing data. Okay, the missing sample, right? So here if you see this result, if we execute this, okay, if we execute this, okay, we will be able to show you this data. okay, this graph, okay. So please try to first concentrate upon this interpolated result. This one is the interpolated data, okay, and here the downsampled version, and this one is the original signal, okay. So here you try to see this, okay, because let me keep only this two data, okay. So this is your original signal and this is your interpolated signal. So as I explained you in the previous case that while doing the downsampling we have skipped one sample, okay. So here we can see that in the interpolation we have tried to restore or reconstruct the lost samples. So here we have this sample and we had this sample in our downsample version and we lost this particular sample, okay. So by using the low pass filtering interpolation method, we have tried to reconstruct back this particular lost sample, okay. So here you can see that this magnitude is not equal to the original magnitude. Some information we have lost, okay. Again, because after this sample and this sample, we lost this particular sample, okay. This was the original sample, but again, we are trying to reconstruct in between this lost sample, but again, that magnitude is not equal to the its original magnitude. So basically, those samples that we have skipped, we are trying to reconstruct it, and we will be reinserting into this particular sample, and by that way, we will be increasing the sampling frequency, okay. So this way our means interpolated signal will look like. Now you can see that if we do the interpolation, right, if we do the interpolation, in that case what happens due to interpolation, if you see this spectrum, okay. So our original spectrum of the signal was this, right. This is our original spectrum, okay, of original sequence section. And now after interpolation, you can see this, we are going to get this particular spectrum. Again, you remember it is plotted for 2 pi, okay, entire 2 pi duration, and therefore we are getting this side also, okay. Otherwise, we would have got only up to this point, right? So here you can see this, we are going to get this particular signal. And if you see this peak again, this peak is coming about 1.25, but you can also observe this another peak, okay. So basically what happens is this is coming due to the non-ideal characteristics of your low pass filter, okay. Because I have shown you that in the case of downsample version of your signal, okay, we actually got these two peaks, okay. In the original spectrum, you will be getting these two peaks, right? So one peak is at this point and another peak is at this point, okay, at 3.76. So normally when we construct a low pass filter, you will find that because in the low pass filter, to pass this particular frequency component, if you design a low pass filter, it will again having a non-ideal filtering operation, and there will be a certain pass band that also allows this particular frequency component. Okay, so this particular frequency component will not be completely suppressed. But magnitude of the means, as we can know that in the pass band, the attenuation of the signal will be very small, but in the stop band, the attenuation will be larger, okay. So within this transition band, it will allow a certain amount of signal to pass through it, okay. And therefore, its magnitude get reduced, but it is not completely removed, okay. So by proper care of designing the filter, we can easily remove this component, okay. So here you can see this value is coming around 3.76. So again, you can see this component, right? This component is also, if you see, it is coming around 1 point somewhere 1.73759. Okay, so this component will definitely come, right? This component will definitely come. You cannot remove this component. It will available, right? So that you have to take care while designing your filters. Fine. So this way you are going to get your reconstructed signal. And one more thing that I would like to mention here is about the this frequency component that we are going to get onto the Y scale. you can onto X scale that you can also get in your original analog frequency. Okay, in terms of original analog frequency component. Okay, so to get that, if you write here the sampling frequency value, so let us say if I write 500 hertz. Okay, so if I write 500 hertz, and I have already solved this problem here. Okay, so if you write 500 hertz there as the sampling frequency, then this corresponds to analog frequency equals to 100 hertz. Okay, so if you execute this code here, okay, you can see this spectrum. Okay, here you can get this spectrum at this point. Okay, so here you can see this spectrum is coming at 100 hertz, right? At 100 hertz, we are going to get this peak. So here everywhere you can, if you substitute the sampling frequency, you will be able to get the W in terms of analog frequency. So I hope you have must understood how to perform this experiment. So we can stop this discussion at this moment. So please try to implement this code onto MATLAB and try to verify the result. So thank you for watching this video and stay connected with the channel. Thank you.